Today, I will continue on basically where I left off yesterday. So just as a brief reminder, I talked about amplitudes in string theory. I sketched the overall idea of what amplitudes are in string theory, and I explained how when you try to calculate them, you have a lot of help from symmetries that put strong constraints on amplitudes, and this naturally leads you into the world of automorphic forms. So that I took as a motivation to study automorphic forms more deeply, and in particular, Eisenstein series on higher rank groups and their Fourier coefficients. And so the plan for today is to take one step further in terms of these Fourier coefficients. So I basically explained how to calculate a particular type of coefficient yesterday, but I want to briefly hint on a more general class, and they are more difficult to sort of get a hold on. And one way to do that is to restrict to some very special types of representations. So I emphasized the connection between representation theory and automorphic forms, and you can focus on a certain class of representations that are also highly motivated from a string theory perspective. So I will discuss what these are, and then I will present some results that we have on Fourier coefficients in this setting. And then in view of time, I may or may not be able to cover part 3, but if I do have time, I want to say something about the possibility of extending these results to infinite dimensional Lie groups or Kac-Moody groups. So we'll see if we get there or not. And then I want to end with some open questions. So that's the plan for today. So I want to continue this discussion of Fourier coefficients with just a one slide reminder from yesterday. So what I did was I first talked about the specific example of Eisenstein series on SL2R. Now, for those that are very familiar with this or familiar with modular forms, Fourier expansions, of course, they come for free because we have this periodicity when you can shift your parameters. So there's this periodicity you can diagonalize, and so you have a Fourier expansion. Now, when you go beyond SL2, you don't just have a one direction in which to expand. You have a higher dimensional space of possible directions in which to Fourier expand. The way to do it is to choose a unipotent subgroup. So this is yesterday I used the letter N to denote the largest unipotent group that you can have. So that the way to think about that is to take basically, let's say if you have S at the group SLN, this is the group of purely upper triangular matrices with just ones on the diagonal. So then the Fourier expansion is sort of the complete expansion. It's expanding as much as you can. And in this particular case, you can get a very good handle on a class of coefficients called Whittaker coefficients. So these are the ones defined here. So that you introduce Fourier modes or these unitary characters, which you can realize explicitly as just e to the 2 pi I sum over integers mj and some variables x that are real valued. And so this is like a Fourier mode with many different directions. Of course, you can restrict if you want to. Let's say I put all of the variables m to 0 except 1. Well, then it's sort of a maximally degenerate character, or you take all of the m's non-vanishing, and then it's a generic character. Now, in the case of generic characters, we know that we can calculate this Whittaker coefficient in very powerful methods using the so-called Kasselman-Shalaika formula and so on. Now, so what I also did, I motivated that from a point of view of string theory, we want to be able to calculate more general coefficients where we don't have this unipotent radical n of the Borel subgroup, but you may have some other parabolic subgroup with another unipotent, and you want to have access to that Fourier coefficient. Now, that's also interesting from a mathematical point of view because, well, one reason is that there is this notion of automorphic descent, which is when you have an automorphic form on some group, you can take a Fourier coefficient with respect to some direction, and that could give you an automorphic form on a smaller group. It is sort of opposite to doing an automorphic lift, like a theta lift or something like that. So there are some motivations for looking at more general types of Fourier coefficients. I'm going to now, from now on, and for a few slides, I will use this language of Adele's that I introduced yesterday. It's not necessary, really. It's just because of the results are formulated in that way. Feel free to just replace A here with R, and you can replace Q with Z, and you can just think of it in this setting instead, real valued matrices and integer valued matrices. It doesn't matter for the purpose of what I want to say. So suppose we do have a standard parabolic, meaning that it contains the Borel. So remember that the Borel subgroup is decomposed into A times N, where N is the upper triangular part and A is the diagonal part. For a parabolic, you instead have this so-called Levy decomposition, where U is the upper triangular part, and L is the Levy, and L will be some reductive group, and it's not just diagonal, it will be some more complicated group. So I will give some examples later on. Then what we can do is we can say, well, if we have an automorphic form, call it phi, you can introduce the U coefficient. So it's exactly the same type of integral that we had before. It's just that I'm now, instead of integrating over this quotient n of r over n of z, I'm doing this more general quotient of the unipotent u of this parabolic p. So this is sort of a class of integrals that's known as unipotent period integrals. And it's a hard task to calculate these in general. So let me just mention some properties. Well, these are not Eulerian in general. So remember, I talked about this generic Whittaker coefficient that at the end of the day, you could actually factorize them into an infinite product over primes. So that's not something that we can prove, is known how to prove in this situation, even for generic psi. So there is no Kasselman-Chalaika formula for the p-adic part and so on. The coefficient is equivariant with respect to shifts on the left with this an element in U. So this is analogous to the case of the Whittaker coefficient. Now, the one idea to try to address these is to try to choose a special type of automorphic representation. So I've just said here I have some automorphic object phi. I haven't said anything about what it is. So what we want to do is get some inspiration from string theory, where special types of automorphic forms appear, and then we want to analyze this type of integral for that class of objects. So that's what I will turn to now. And this brings me into this notion of small representation. So what do we mean by that? Well, there is a definition that goes back to many people. I think the one I took here is from the seminal paper of Ginsburg, Rallis, and Sudri. So they say that an automorphic representation, typically called pi, is minimal if each factor in this product over primes has smallest non-trivial Gelfand-Kirillov dimension. I think by now one would say that actually all of the factors should have smallest non-trivial Gelfand-Kirillov dimension. I think GRS were a bit careful back then. So remember, yesterday I talked about what is Gelfand-Carrillo dimension. It is the notion of a functional dimension of the representation. So basically, it is the smallest number of variables on which the functions depend. But for our purposes, there is a characterizing feature, namely that if you have an object in the minimum representation, it's characterized by having very few non-vanishing Fourier coefficients. So the typical example would be a theta function. So theta series are sort of simple examples of these kind of objects. I was planning to go through some details about theta series here, but in view of time, I decided to skip that. But you can read about that in the book. So I want to look at some other types of examples. But before I do that, let me just say something about what's going on in the physical interpretation of this. So remember in the beginning yesterday, I talked about how you could have an amplitude of, let's say, 4 strings scattering, and that could give rise to a correction term in the effective action. So I call that the R4 correction. R4 would be the 4th power of the Riemann tensor. So this is a correction to gravity. And you have these functions in front of the correction terms, F0 and F4, and they are the automorphic forms. So I focused on this yesterday, the situation where you have an Eisenstein series, depends on a single parameter, S, and it turned out that for S equal to 3/2, we got an exact match of the expected leading term and the expected differential equation and so on. So there was a unique Eisenstein series that gave rise to this coefficient. So that story actually generalizes, and as has been pointed out, in particular by Green, Miller, Van Hove, and Boris Piolin, there is a class of Eisenstein series in each dimension. So these integrals here, I've denoted it 11 minus n. It's because we have this compactification on a torus, and for each, when n becomes bigger, the symmetry group becomes larger. But in each case, the couplings or these coefficient functions are given by Eisenstein series with a particular value, s equal 3/2 in the top case and s equal to 5/2 in the lower case situation. Now you can argue that this means that the functions corresponding to the top line here are really corresponding to minimal automorphic representations. And from a string theory perspective, they are called 1/2 BPS. The second line for the coupling is d to the 4, r to the 4, so it's a 4th derivative acting on these Riemann tensors. That is attached to a slightly larger representation called the next to minimal. So I will mainly focus on the minimal case here. I will make some remarks on the next to minimal case, but there is this very interesting interplay between the conditions that come out of string theory and these automorphic representations. So I think this gives strong motivation for studying this further. So what we did in a paper some years ago is to say, well, if we now take just the case of SLN, what can we say about these Fourier coefficients if we look at the minimal representation? So again, here, it's perfectly fine if you want to think of SLNR instead of over the Adels. F here is a number field. You can think of it as Q if you want. Doesn't really matter so much. The Gelfand-Carrillo dimension in this case of SLN is n minus 1. So for the minimum representation, so let's say we have SL3, the Gelfand-Carrillo dimension of the minimum representation is 2. So it's 2-dimensional, and that's in contrast to the generic representation, which has Gelfand-Carrillo dimension 3. So it's one less dimension. So our main theorem here is that we could show that for any automorphic form attached to the minimal representation, you can actually write the complete Fourier expansion in this very, very compact way. So the first term here is the constant term. I think I called it E0 or something in the slides yesterday for the Eisenstein series. Then what we have is a finite sum of terms that are sums over this gamma. Gamma I is an element in this coset here, where you take SLN minus I divided by the stabilizer of a vector with just a single element non-zero. There is element 1 in the position I. So what you should really notice here is the psi alpha I in the integrand. So that's a crucial point here, that this psi is not a generic character. In fact, it's the opposite. It's a maximally degenerate character that has only one non-vanishing direction, namely in the direction of the simple root alpha I. So that's a feature of the minimal representation, that it basically collapses all the other Fourier coefficients to 0. So if you know about the Piatetsky-Shapiro-Shalaika expansion of cusp forms of GLN, you can think of this as sort of an analog of that, but the structure is slightly different, and it emphasizes this particular property of the maximally degenerate character that will play a role shortly. So what we have here is the complete Fourier expansion, but I kept emphasizing that we want to have specific coefficients corresponding to different unipotent radicals, because that's interesting both mathematically and from a string theory point of view. So can we use our result to access that? So suppose we focus on some maximal parabolic subgroup now. So yesterday I explained what this is. It's the parabolics that you get if you pick a single simple root. Let's say you have a Dynkin diagram and you pick a single simple root and remove that, then what you have left will be the Levy L, and that will determine your parabolic subgroup. So we have a theorem in our paper that for any element in this pi-min, if you have a maximal parabolic, then the Fourier coefficient vanishes if the rank of this unipotent is larger than 1. So that basically means that it's not maximally degenerate, and only if the rank is exactly 1, you get this particular expression here. And this is quite surprising, because if you notice that on the left-hand side, this is really a Fourier coefficient that is a coefficient along U, but you can calculate it directly as an integral over the unipotent of the Borel. So this is a huge simplification, because the right-hand side here is calculable. And indeed, you can show that this is Eulerian. So you get access to these U coefficients that are much more difficult in terms of the coefficients that are essentially what I called yesterday degenerate Whittaker coefficients. Okay, so what can you do with this? Well, I want to give you an example, because this may be a bit abstract. So I'm picking the example of SL5. So then you see if I pick SL5, I remove the outmost node. What I get left as the Levy is SL4 times GL1. You see the unipotent here. And the character psi u, which is just now maximally degenerate, it is non-trivial only on this part down there, this X. I'm picking it in this way. So even though I'm on SL5, this whole character only takes the form e to the 2 pi I kx. Again, feel free to think about x as a real variable and k as an integer. So this is a rank 1. And then what happens with this complicated U coefficient, it basically collapses to this very simple expression that we recognize from the SL2 Eisenstein series. Is a modified Bessel function of a particular order. There is a divisor sum of a particular order. And this is the complete coefficient. Now, if you're familiar with string theory, if you now restrict to S equal to 3/2, you can recognize this as capturing the contribution of certain instantons, in this case, M2 brane instantons in M theory compactified on T4, where the instanton measure is precisely what you get here if you fix S equal to 3/2. So that's one way of sort of using this mathematical machinery to extract some information that we want to have from physics. So this was all for SLN. So what can you say more generally? So I'm not going to go into too many details, but we have, in collaboration with Henrik Gustafsson, Dima Gorevich, Axel Kleinschmidt, and Siddhartha Sahi, generalized this in quite a few directions, but let me just stress one here. So if you have a simply laced Lie group, semi-simple, simply laced Lie groups, then in fact, all Fourier coefficients are completely determined by degenerate Whittaker vectors of this form. And so what I've done now, I've sort of snuck in a phi in NTM. So this is the next to minimal representation. I have had planned to have a theorem for the min rep first, but it doesn't really matter. So if this would be the minimal representation, then only the first equation would play a role. But when you go to the next to minimal representation, you also get Fourier coefficients that are determined by these sort of next to maximal degenerate Whittaker coefficients that are non-trivial on pairs of simple roots. And here it's important that these are simple roots that correspond to Lie algebra generators that commute. So these are commuting simple roots. So this means that you can sort of write any Fourier coefficient as a linear combination of these simpler objects. So this generalizes earlier results of Ginzburg-Rallis-Sudry, Miller-Sahi, and so on. I'm going to come back to that a little bit later because Ginzburg-Rallis and Sudry did this for exceptional groups, and I want to comment on that a little bit later. So this is the kind of powerful results that you can get when you focus on these simple types of representations. From a physics point of view, the distinguishing feature on going from the minimal representation to the next to minimal representation, that really has to do with if you're looking at 1/2 BPS effects or quarter BPS effects. So we are working now on trying to really extract quarter BPS couplings from this result, and hopefully that will come out at some point. So I want to talk a little bit about exceptional groups because I like them, mathematicians tend to like them, and we can sort of focus on just E6, E7, and particular E8, and say something very concrete about these results. So,
sorry if I can just interrupt.
Yep.
So all the groups that you're considering are simply laced, or is it that these are the ones which appear in U-duality?
So we have the general result that I showed before are for simply laced groups. We have results that are more general, but I'm a little bit careful because I can't make as strong a statement. I don't see any particular problem. It's just that when we did this, we focused on that case because it was sort of a little bit easier and more relevant for string theory and so on.
I see.
Yeah.
Thanks. Thanks.
So let's look at exceptional groups. The Gelfand-Carrillo dimension of E6, E7, and E8 are written here. So let me take the example of E8 for definiteness. So you can take a grading of E8 in this way. So E8, the Lie algebra of E8 has a 5 grading. So that means that there is a Cartan generator corresponding to the 1 here in such a way that you can, the other, the 56 and the 1, they sit in representations of E7 like this. And actually the minimal representation, which is 29 dimensional, you can think of that as a symplectic slice in the 56, 28 dimensional subspace there combined with the 1. So that's essentially where the minimal representation lives. So you can have the group action on functions of these 29 variables. The generic situation for this particular grading would be to have a 57 dimensional representation, but the min rep will slice that into 29. So what does this mean in terms of automorphic forms? Well, this is what goes back now to Ginsburg and Rallis and Sudri, who were the first, I think, to do this in terms of automorphic forms. So if you take an Eisenstein series, a Langlands type Eisenstein series that I defined yesterday, and you pick the particular weight lambda in this way so that you have 2s minus the fundamental weight corresponding to the first simple root, and then you pick the value s equal to 3/2, then you can show that the complete Fourier expansion of this, I cheated a little bit, so I'm sorry about that. This is for any of the exceptional groups, this E2s minus lambda 1, this min rep for s equal 3/2. The Ginsburg-Rallis-Sudri result is for E7. So when you look at E7, you can write the complete expansion in this way. So you have the constant term, and then you have a single sum over this orbit here, the Levy, and then the stabilizer of the Levy of this particular character corresponding to alpha 7. Now, if you look at this, this is quite remarkable because the dimension of this stabilizer that you have is precisely 17 dimensional, which is the dimension of the minimal representation. So you see that the functional dimension is directly telling you the minimal number of variables in which you can realize the Fourier expansion. Now you also notice that the coefficient f psi alpha 7 that were in the GRS result, it is a maximally degenerate coefficient because the character psi feels only the single simple root alpha 7. So you can view our result as it generalizes this because we show that any such automorphic form is completely determined by these maximally degenerate coefficients. Yes. So this shows that you can get a lot of explicit results if you restrict representations in this way. And a lot of the motivation from a math point of view have also been in terms of theta lift. So in particular, David Ginsburg has done a lot of work on how minimal representations can be used in terms of lifting automorphic forms from one group to another. That also plays a role in string theory, but it's not really what I want to focus on here. What I like to do is now say, okay, actually, it makes sense from a string theory point of view to try to ask what happens if you go to infinite dimensional groups. Which of these results can you hope to recover? And there are some really cool stuff that I don't think mathematicians know about, so that's why I wanted to highlight it here. But maybe before I go there, I should stop talking for a little while and see if there are questions or concerns or.
So sorry, maybe it's just some naive question. So you said you want to extend these considerations to infinite dimensional groups, that is like the group of the Kac-Moody algebra,
Yeah. Yeah.
I see. And okay, maybe you should just go on, and then maybe I'll have questions after that.
Yeah. So I mean, it may seem like a crazy thing to do, but in fact, from a string theory point of view, that's a very natural question. So I just want to remind you again about this table that we had yesterday. So this is the list of symmetry groups that we get in different dimensions in string theory. So this is, of course, the reason why I picked a particular example of SL5. I focused on E6, E7, and E8. They appear in these different dimensions. So you see, we start all the way up from 10. We go down to 3 dimensions. And it's natural to ask, well, what happens if you go further down? Well, then we have these conjectures that the groups become infinite dimensional. So if you continue to 2 dimensions, 1 dimension, or 0 dimensions, we get the groups E9, E10, and E11. So E9 is an affine Kac-Moody algebra or group. It is an affine extension of E8. E10 is a hyperbolic Kac-Moody group, and E11 is a so-called Lorentzian. Now, also here, we expect to have arithmetic symmetries, so we should somehow have discrete subgroups of these that play a role. So for a long time, physicists have asked questions, can we extend some of these results to Kac-Moody groups? Well, then, first of all, the mathematical theory is not even remotely sort of developed in the same detail. You do expect to find new exotic physical effects and so on. So there are many issues, but you could just sort of plunge ahead and see what you can do. That's often the path taken by physicists. So let's see where we get if we do that. But I want to give just a little bit of history of what has been done. Of course, I'm neglecting some things, but actually already in the mid-90s, Kapranov had a paper where he was motivated by physics, but sort of quantum field theory, so-called Vafa-Witten theory. He constructed certain geometric Eisenstein series on loop groups, or affine, essentially affine Kac-Moody groups. Then Howard Garland could extend the definition of Langlands type Eisenstein series to loop groups in the case of number fields. And he proved convergence and so on. So that was sort of maybe the starting point of trying to develop the whole theory of automorphic forms on Kac-Moody groups. Then in 2005, Freydoun Shahidi wrote a paper where he suggested also the Eisenstein series on Kac-Moody groups might be a source of new L functions. So that also was some motivation to continue that study. And then actually Manish Patnaik in his PhD thesis under Garland showed that Kapranov's and Garland's constructions actually agree if you have the same underlying field. And then in 2013, not because it's like at the same level, but because it's relevant for this, then we wrote a paper where we calculated explicit Fourier expansions of Eisenstein series for certain Kac-Moody groups. And so I want to talk about that result, and I want to put it in sort of the light of today's talk and try to interpret it and see what we are trying to do with that old result today. So that's sort of the history. Now, I'm not going to give you an introduction to Kac-Moody algebras, but they are Lie algebras. If you're familiar with the Chevalier construction of a Lie algebra from a Cartan matrix, you also know that if you have the Serre relations, eventually when you take commutators, they are killed, and that's exactly what gives you a finite dimensional structure. When you go to the Kac-Moody case, that doesn't happen, so the Serre relations are not enough to kill the commutator, so you can continue indefinitely in some directions. So there are actually no classification of Kac-Moody algebras in general. There are classifications of subclasses like affine. Hyperbolic are classified to a certain extent. I think well, no, sorry, hyperbolic are completely classified, but beyond that, there is no classification. So the main way to think about what happens is that for a finite Lie algebras, the killing form on the Cartan subalgebra is Euclidean, and then that's a Euclidean signature. When you go beyond up to hyperbolic and so on, you can get minus signs, so you get Lorentzian signature and so on. And that brings in imaginary roots, namely roots that square to a negative number. So I have one picture just to give you an example. So there is the hyperbolic Kac-Moody algebra known as A1++. You can think of it as an extension of SL2, like having SL2 on the rightmost node. You extend it once to the affine extension of SL2, that is the Dinkin diagram with two lines. There is a prescription for extending one more time. You get this Cartan matrix here, which has Lorentzian signature. And there's a nice way to picture this pictorially. So you can just think of decomposing
Sorry, I'm not hearing anything anymore. Are other people hearing him?
Oh, I'm not hearing anything.
Yeah, so I think his connection has somehow frozen.
So now he will.
Yeah, okay, he's back. You're muted
You
though.
are
You have to
muted.
unmute yourself. You're muted.
Yeah, there was some Zoom issue, so I just went back. I'm going to.
Okay.
I don't
No
know
problem.
what happened with Zoom. Sorry about that.
Yeah, no, sure.
So this is just a way of seeing sort of where this infinite dimensional structure comes from. But what can we do with this? Well, we can say, well, why don't we just define Eisenstein series in the same way? Okay, you could do that. You have an Iwasawa decomposition, so you can construct the Eisenstein series formally in the same way. So what is the arithmetic subgroup? You can define it as a Chevalier group, basically in terms of exponentiating Lie algebra generators with integer coefficients. So you can define that g of f here, I want to have as g of z in this case. You can do it for any number field, but I want to restrict to the integers here. Now, convergence of this is, of course, a big issue. I mean, Langlands wrote this big volume on convergence of Eisenstein series in general. So here, convergence was established by Garland in the affine case. For rank 2 hyperbolic, it was done by Carbona, Lee, Liu. There are actually some follow-up works that I forgot to cite by Miller and others, but the general case is open. And also some results on constant terms that has been established by Garland. Okay. Braverman, Kashtan, and Patnaik has done a lot of work in the function field case. So that is a situation where you can prove more things. Garland, Miller, and Patnaik has nice results for Eisenstein series with no constant terms. So they are cusp forms, so they are not so relevant for our string theory interpretations. And then I want to focus on what has been done for Fourier coefficients in this case, because there is an interesting connection to representation theory lurking there. So one thing that I want to stress now, what are the differences from the finite case? Well, first of all, the Borel subgroups for Lie algebras, the Borel subgroups of upper triangular matrices and lower triangular matrices are conjugate. You can get from one to the other essentially using the fact that there is a longest Weil word in the Weil group, and you can go from one to the other using that. But for Kac-Moody groups, the Weil group does not have a longest Weil word. It is not a finitely generated Coxeter group. So this means that you could imagine constructing Eisenstein series from B plus or B minus, and they're called positive and negative Eisenstein series. In the finite case, they are the same, but this is not clear in the Kac-Moody case. Now, Braverman and Kashtan have shown that they are actually related by a functional equation over function fields, but the same is not known for the case of number fields. So that's the situation. Another interesting fact is that when you try to define Whittaker coefficients, so you want to look at Fourier expansions in the same way, what happens, I showed you yesterday that when you have generic Whittaker coefficient, there was this famous result that the entire sum that is in the Eisenstein series, the only contribution from that after unfolding comes from the longest element of the Weil group. There's just one term surviving, and that's why you have this nice factorization into product over primes and so on. For Kac-Moody groups, there is no longest Weil word, and actually the entire generic Whittaker coefficient vanishes identically. So there is just nothing there. It's empty. So what you can do, well, you can say, like, if we look at the finite dimensional case, what you can do is you can see, okay, you have this W0 inside, but W0 acting on n will take you to the opposite in the finite dimensional case. So you can interpret this integral here as an integral over the opposite n. This is all in the finite dimensional case. So Braverman and Kashtan said, well, we should just add by hand this integral in the Kac-Moody case. Sort of say, well, we can't access it through the longest Weil word, but we can add it by hand and try to compute it. So that has been done, and Patnaik proved an affine generalization of the Kasselman-Shalaika formula, but we don't really know how to do this for the real numbers. But our take was, okay, you don't have a natural access to this generic Whittaker coefficient. What about the degenerate cases? Because we have seen from our studies in the minimum representation that many cases when you have restricted the parameter space of your Eisenstein series, it's the degenerate coefficients that are playing a role. So let's see what you get if you focus on degenerate Whittaker coefficients. So we proved a formula that looks a little bit complicated. Let me just guide you through it. So if you have a Whittaker coefficient W, and now you say that psi here is not a generic character, but it's a character that is generic on a subgroup of G. So this means effectively that only some of the directions of a simple root are non-vanishing. So the simplest and most degenerate case would be if psi is just psi alpha, where alpha is a single simple root. So effectively, this means that the degenerate Whittaker coefficient is a sum over a certain subgroup of the Weil group. And the elements here, W psi G prime, they are Whittaker coefficients that are generic on a particular subgroup. So they are something we can calculate explicitly. And the M's are certain coefficients that are basically ratios of Riemann zeta functions. So it looks complicated, but it's a formula that you can calculate explicitly. You can put it on the computer. And so that's what we have done for certain cases. And let me give you, so here is this intertwiner. It's a product over ratios of Riemann zeta functions. It's exactly the same factor that appears in Langland's constant term formula. So what do we get in some example? Let's take my favorite example, E10. This is this rank 10 hyperbolic algebra. Now, quite remarkably, this Eisenstein series for E10 should have an infinite number of Fourier coefficients for each character, because it's a Kac-Moody group. But what happens is that when you fix this special value, so again, we have this general complex character in the complexified weight space, this lambda. If we now fix it to this special character, the special value that we had before, motivated by string theory, then what we see is that the entire sum collapses, and the only non-vanishing Whittaker coefficients are the ones corresponding to maximally degenerate characters. So in the leftmost column, I've listed these characters psi. So it's non-vanishing in the first direction or in the second direction and so on. So this is like psi only feeling the first root. The second line is psi only feeling the second root and so on. And then in the right column, I've given the explicit expression of these coefficients for this value in terms of this function b. And this function b is essentially the divisor sum multiplied by the modified Bessel function. So you have this sum with only these 10 non-vanishing coefficients, and all the rest is absent. And this is due to the vanishing properties of the intertwiner. So there's nothing else. So you have this infinite number of potential Fourier coefficients, and all of them vanish except for these ones. So of course, you want to try to understand what this means. And so our conjecture, very natural conjecture, is that at least for E9, E10, and 11, where we have these checks, then this Eisenstein series should be attached to a minimal representation of these Kac-Moody groups. Now, the problem is that no one has really defined what minimal representations mean. There is not even a notion of automorphic representation that is properly understood for this. But it's just that the actual computations really hint at something like this being ongoing. One thing I can mention is that a key element in understanding these representations that I haven't really focused on so much is the notion of nilpotent orbits. So you can classify these representations using nilpotent orbits. So this is the orbit of the group of some Lie algebra element. But that's also a case that for Kac-Moody groups, there is no good understanding of what a nilpotent orbit is. Is it infinite dimensional? How do you characterize its size and so on? So we are trying to understand some of this from a representation theoretic viewpoint together with Guillaume Bossard, Axel Kleinschmidt, Manish Patnaik, and Siddhartha Sai. So we'll see if we get somewhere. but I think this is very interesting, and it points to the existence of this kind of representations also in the Kac-Moody setting. Now, one thing that I haven't really included here is that you can go ahead and now try to focus on the particular coefficients we have and extract their physical properties. And you do see that you get instanton effects that are sort of exotic, if you want. They go like e to the minus 1 over higher powers of the string coupling. So this is what you would expect, for instance, of D7 brane instantons and so on. And you can see that they seem to be there in these Eisenstein series. I just want to go a little, yeah, so I want to say a few more things, just what it indicates mathematically. So it hints to also that the minimum representation, whatever it is, should be Eulerian, and that the only non-vanishing Whittaker coefficients are maximally degenerate, and they are also Eulerian. So you get all these properties out of this that should have a bearing on the representation theory, and this particularly indicates that we should be able to treat this problem locally. So we should be able to think of a p-adic representation and maybe try to understand it in this way. So that's what we are thinking about. Yes, so I think that's what I wanted to say. Are there any questions about this part before I talk about some open questions, so on?
Yeah, I have a general query not related to this, that this a lot of mathematics is there, advanced mathematics and representation theory is being used in string theory. That's what we see. And these non-compact groups, are they natural objects of study in string theory, or initially this was done for compact groups and slowly one is going towards non-compact groups, or I mean, what is the situation?
Sorry, what did you mean by non-compact groups? I think all of the groups I talked about are non-compact.
Yeah, that's right. They are all in your talk. All these are non-compact groups.
Okay. I see. Yeah. Okay. So this is in this. So what I guess I can show you this picture. So actually, what does happen is that you have a non-compact group as sort of the global symmetry of the theory, and those are the groups that I call G here. But you also have what we call a local symmetry that's given by the maximal compact subgroup. So these K groups are compact groups that are also symmetries, and that's why you actually get what we call functions that are spherical. So they are always invariant under this SO2 group, for instance, and so on.
Yeah. So in
I don't know if that's what you
are
meant.
very natural objects are global. These groups, non-compact groups are the natural objects of study, and in particular, you require, of course, compact groups and then like that. So that's why I wanted to.
Exactly. Yeah.
Right. At the end of, with the permission of the chair, I want to give some general remarks about the. Yeah, I mean, anything else, any other discussion is there about this talk, then after that?
But you haven't finished, right, Daniel?
No, I have some open questions and so on. So I just wanted to, before I go there, I wanted to just check if there are some questions.
So Professor Khatri will make some remarks after you've done.
At the end.
Go ahead.
Yeah. Okay, so I have given you this sort of, if you want, a brute force calculation that we have, and then I am giving you an interpretation of what it might mean mathematically. So I just want to give you some open questions here and also some open questions from yesterday. So I think there are many interesting directions to pursue in terms of this Kac-Moody case, that you can think about what are the p-adic representations how do you understand them? Well, there is a good understanding in the finite dimensional case that the p-adic components of an automorphic representation is really a representation of the spherical Hecke algebra. And you can hope that there is something like that for the Kac-Moody case, but then a more complicated objects like the double affine Hecke algebra could play a role. So I'm not an expert on that at all, but this is what has been suggested by various people. You also have this issue of the differential equations, right? We do have the differential equations satisfied by these Eisenstein series. One particular feature of the minimal representation is that you actually get a smaller ideal in this context. So there are stronger conditions coming from differential operators. And for the minimal representation, this is famously known as the Joseph ideal. So you can hope to analyze if there is some analog or some generalization of that in the Kac-Moody case. There has been some results by Garland and Liu on studying theta correspondences for Kac-Moody groups. That's something that will be very interesting to look at from the point of view of our results. So these are some open questions that we are thinking about in this setting. But I want to also bring out one interesting point that more connects to the talk yesterday. Maybe some of you noticed that when I looked at these objects, I only looked at r to the 4, and then there was d to the 4, r to the 4. So I looked at two types of corrections, right? But in my diagram, I had this diagram of the two-parameter space of couplings of string theory. There was this genus expansion on the y-axis, and then there was the alpha prime expansion on the x-axis. The alpha prime expansion actually corresponds to this. You can think of it as related to these derivatives. So what if I take higher derivatives and not just d to the 4? What happens then? Well, actually what happens is that you get new types of automorphic objects that are not really studied by mathematicians before. So it's known, for instance, that when you go to the d to the 6, r to the 4, string theory predicts that the coefficient should be a function f of tau that is not an eigenfunction of the Laplacian, but it has a source term on the right-hand side, which is the square of a non-holomorphic Eisenstein series at E3 halves. So it's kind of like a Poisson-type equation. So from the point of view of automorphic representations, this violates the Z finiteness condition that we have. Well, going back to Harishchandra, really, that automorphic forms should be eigenfunctions of the ring of invariant differential operators on the group. That's no longer true. But they are still interesting, and we now know there is a bigger class of these objects and so on. So it really begs the question, like, is there a representation theoretic origin? How should we think of them in the big scheme of automorphic forms? So that's a big open question that I think mathematicians should take an interest in. So we are currently working on understanding some aspects of the representation theory with Guillaume Bossard, Dima Gorevich, Sol Friedberg, and Axel Kleinschmidt. And yeah, but I think there are many interesting things to study when it comes to these new automorphic objects. So I think I will stop there and invite questions, comments.
Thank you very much. I have a couple of questions and comments, but first, does anyone else have a question? So maybe my questions are a little general, but you talked of r to the 4th and d to the 4th, r to the 4th corrections in the low energy effective action of string theory. And just now we talked of d to the 6, r to the 4th. And just wanted to understand, so what is the status with higher powers of r, or is that not at all in the frame? I mean, you looked at higher derivatives, but still fixing fourth powers.
Yeah. So there are some works done, but very little, in particular when it comes to these automorphic forms and so on. I would say that it becomes sufficiently complicated when you just look at d to the 6, r to the 4, and so
Of
on.
course.
Of course, you can look at, as you mentioned before, you can look at the fermionic versions of the same multiplets and so on. But when you really go to higher powers of the Riemann tensor, yeah. I think what we need is we need to understand somehow the structure of these new types of objects, because at the moment it's sort of a little bit like a trial and error. You find this, but you don't have a framework to put them in like we do for the automorphic forms.
I see. And r to the 4th is the lowest non-trivial order beyond r, right? Because in superstring you don't have r squared and r
You don't
cubed.
have r to
So
the
this
second
really
power.
looks like, as you say, it's very complicated, but looks like the beginning of a much bigger question.
Yeah, there must be some bigger structure there, and I think we are. I mean, there is this beautiful story, right, of automorphic representations that is lurking at these lower levels, but somehow we need to replace that or to augment that with something when we go to beyond that. And
I see. So let me ask, Michael Green and company were sort of the ones to start off in some way this study of higher derivative corrections and relation to modular forms, right, in string theory.
Yes.
And,
I mean, Green and Gutperle in particular were like the first
that
paper.
was the first paper. I even remember when it came out.
Yeah.
But have they is there any context where they have gone beyond r to the 4th, or are there, or is all there, was that work just on r to the 4th?
So the first work of Green and Gutperle was only r to the 4, but then there have, of course, been many follow-up papers, and I think Michael Green's what's his name, postdoc Anirban Basu,
Yeah,
he has done a lot of work as well, which I think goes beyond what I presented here.
Right, I know Anirban well, and actually he has been working on this for years. Probably I should look at his papers.
Yeah, but he has some very powerful, very complicated papers that
I see.
go pushing this a lot. So I think our perspective now is to try to look at sort of the simplest non-trivial case beyond automorphic forms and see if we can sort of get a handle of the mathematical structure there.
Right. And my second very brief comment was that, you know, in the U-duality groups which appear in appeared in your table are those of type 2 superstring theory. But there is also a curious phenomenon with heterotic strings, which is that if you go below 6 dimensions, below 4 dimensions, that is, you compactify on a 7 or 8 torus, you start to get a U-duality group in 3 dimensions and then a Kac-Moody group in 2 dimensions.
Yes, right. So in 3 dimensions, you have SO 8,24.
You have O8,24, which unifies actually what you expect, namely O7,23, that is T-duality, with SL2.
Right.
And then it becomes fine if you go 1 dimension lower, which is a bit reminiscent of your more fancy.
Yeah, I agree. So actually, that's good that you mentioned. So I should have mentioned that there are papers with Boris Piolin, by Boris Piolin, Guillaume Bossard, and students looking at some automorphic forms in those settings with these big U-duality groups that are orthogonal, non-split. And so that's on the heterotic side is sort of, in some sense, more complicated because those are non-split groups because they have this SO824 structure.
Right.
Yeah.
Got it. I see. I thought it might be simpler in one way because in 2 dimensions, it's just SO824. So it's affine, even if it's non-split.
Yeah, that's right.
Kac-Moody. It's not
anything but it's sort of the structure of the root lattice is more complicated. So it's, yeah.
I see. Okay, well, thank you very much. And really thank you from all of us for your talk. For your 2 talks, very nice talks. And now Professor Katre would like to say something, I think, because this is the conclusion of a trimester series.
So thanks, Professor Persson and Daniel Persson and Professor Mukhi also. All this series has been very good and many good comments have been received so far from different people. And at the beginning, Professor Devendra Tiwari suggested that we should have a lecture series because of this birth centenary year 2023 of Harishchandra. Harishchandra was born on 11th October 1923, and then he suggested that we should start a series from September 2023. Should be 1 year series, and therefore he contacted uh, experts on representation theory, including Professor Sunil Mukhi, who is here, and Arvind Nair, E.K. Narayanan, Aladi Sitaram, Sundaram Thangavelu. So there was a meeting earlier, and of course, it is difficult to touch all the aspects of the work of Harishchandra, but still, these experts suggested uh, topics which can be considered, which are related to the work of Harishchandra in different ways. And therefore, all these lectures have been split into 3 trimesters, and different topics were considered. For example, in the first trimester, we had Euclidean harmonic analysis, representation theory of compact Lie groups, then Lie groups and Lie algebra, a crash course was there. And then in the second trimester, we had representation theory of SL2R, because that's an important example, which we have, if one knows that, then one knows other things in a better way. So that was considered, and then representation theory of periodic Lie groups, because a lot of work is being done on periodic Lie groups nowadays. Then work of Borel Harishchandra also was considered. And then in the third trimester, there was introduction to Langland's program, then cohomology of arithmetic groups, and now, for example, these 2 lectures were related to representation theory and theoretical physics. So all these lectures are available on the YouTube channel, and slides are also available. All the speakers have been gracious enough to provide their slides, and they are allowed to uh, present the videos for everybody. So we are thankful to all the speakers of this lecture series. And there was an organizing committee for this, and IISER gave good support. And along with Professor Sunil Mukhi, we had Manish Mishra, who took a lot of part in the organization. Especially there were offline lectures which were held in IISER Pune, and then these were all organized by Manish Mishra, with the help from others like Mainak Poddar, who was the head of the department, then Chandrashil Bhagwat, current head is Somen Maiti. So all of them were very helpful. Many other staff members also were very helpful in the organization of this lecture series. And from Pakistan side, Professor Solabrukar was also a member of the organizing committee. And Devendra Tiwari was the chief coordinator for the whole series of lectures. Devendra Tiwari left his postdoctoral fellowship, was over at the Bhaskaracharya Pratishthan, and then Joel Mahajan joined after that, and he actually organized the remaining lectures. And all these were supported by technical committee. So I thank Shyam from IISER Thiruvananthapuram, then Pawan Dodya, he is from Bhaskaracharya Pratishthan, and Kailash Chavan. They helped in the technical committee. And I would like to give a special mention of Professor Dipendra Prasad, who is from the beginning helpful in this series, along with all the professors in the scientific committee. He was also very helpful, and whenever we said you should come and help and also chair the sessions, all that he agreed, and he has done that. Also, I would like to mention this National Board for Higher Mathematics, because the Bhaskaracharya Pratishthan gets support from the National Board for Higher Mathematics. And these activities of lectures in the Harishchandra lecture series are also supported by National Board for Higher Mathematics. So I thank the National Board also. So yes, thanks to all the speakers have done a very good job. And this series in the video form is available on the YouTube channel, and I'm sure it is very beneficial to different people, especially because the work is considered very difficult, at least for the outsiders, those who are not all working in it, for them it is fine, but for others, certainly it is difficult. But how it is connected to different aspects of number theory and group theory and so on. Now, string theory also, I was not very much aware that it is also connected to string theory in this way, and people are using the work of Harish Chandra. So that also is also clear to us by the lectures, these lectures of Professor Mukhi and Daniel Persson. So thank you very much. These are my final comments. Thank you.
Thank you all. It's been a pleasure for me to at least attend whichever lectures I could, and I'm grateful to all of you, including Professor Katre, and of course, especially Devendra Tiwari, who gave a lot of effort towards organizing it, and to all the speakers. So, Daniel, we have to thank you on behalf of 1 year worth of speakers. So please accept our thanks.
Thank you.
And,
I accept for everyone.
Yeah. So bye-bye, and see you all somewhere.
Thank you very much. Bye-bye.
Bye-bye.